Okay, chapter 9. The first problem gives us a golf ball that has a mass of 45 grams. We'll call that 0.045 kilograms, so that we're in the right units. And then it also says that the ball leaves the tee at a speed of 38 meters per second. And then it asks some questions. The first question is, what is the impulse in the golf ball? We know that impulse is force times the change of time equals the change of momentum. So we don't know anything about the force that's applied or the time interval through which it's applied. So let's look at the change of momentum, which is momentum final minus momentum initial, which in this case, momentum final is mass times velocity. So I'll write that, mass times velocity final minus mass times velocity initial. Velocity initial is 0, so the mass is 0.045 times the velocity final of 38, gives us the impulse, which is 1.71. And then I like to use the units for that. I like to use newtons times seconds, just because it's easy to remember, sort of from the formula right here. You could also use kilogram meters per second, because that's what's on this side of the equation. Those are the same thing, those units. But I'll use newton seconds. And then part B says, what is the average force that the club exerts in the golf ball if they're in contact for 2 times 10 to the negative 3 seconds? So we're using the same equation right here. Impulse equals change in momentum. We know the change in momentum is 1.71 newton seconds. We now know the time interval is 2 times 10 to the negative 3, so 1, 2, 3, so 0.002 times the force. So just divide both sides by 0.002, and that gives you a force of 855 newtons. Okay, the next question says, what average force does the golf ball exert in the club during this time? Well, we know that Newton's third law says forces come in pairs equal and opposite, so we know we can do negative 855 newtons for the force the golf ball exerts in the club. All right, next problem is number 5. Gives us a massive crate on a bed of chalk, and it tells us the coefficient of sliding friction. Technically, this should be static friction, not sliding friction, because the box isn't moving at all, so that's a little bit of a problem with the problem. And then also, it's a little hard to imagine the picture that they wanted you to set up. I originally drew it wrong, but apparently the cables go horizontally like this, and they're able to provide tension to keep it from moving front and back somehow. So it's kind of it's just worded really poorly, but that's okay. It says that each of these cables can provide a force of 650 newtons, and the truck stops in 1.8 seconds. What is the maximum speed the truck could have been moving without breaking the cables? So let's draw a free body diagram on this. A free body diagram, we know that there's a tension on the cables which is causing this to stop, which is 2 times 650. Apparently they both can basically pull backwards with this tension, which is not worded in a way that you understand that, so I have to be more clear on a test or a quiz. And then also there's friction, which is technically static friction because it's not moving, which is pulling back as well. So those are the two forces. So if we want to figure out the net force on this thing, it's going to be equal to 2 times 650, which is the tension, plus the force due to static friction. So we can figure that out because that is the normal force times the coefficient of static friction on our formula sheet. Easily written like that. And once we find this, we know that that's going to equal the mass of the crate times the acceleration of the crate. We can use that to find out how fast it must have been going. So let's plug in coefficient of static friction is 0.3. Normal force is mass times gravity. So that mass was 180 kilograms. And gravity is 9.8. I'm going to solve for the acceleration. This is 180 kilograms times the acceleration. Divide both sides by 180. You get an acceleration of about 10.16 meters per second squared. And finally, we know that acceleration equals change in velocity over change in time. So if we know the acceleration is 10.16, we know that it comes to a rest, so final minus initial. We know that the final velocity is 0. So we can just find, technically this would be negative, the acceleration, because it's accelerating opposite direction of motion, so these negatives would end up canceling. So basically we can use the time, and they give us the time is 1.8 seconds. If we multiply both sides by 1.8, we get the initial velocity the truck was going, about 18.3 meters per second. Next question says a singular uranium atom has a mass of 3.97 times 10 to the negative 25 kilograms. It decays into a nucleus of thorium by emitting an alpha particle at a speed. So the speed of the alpha particle was equal to 2.1 times 10 to the 7 meters per second. The mass of the alpha particle is equal to 6.68 times 10 to the negative 27 kilograms. What is the recoil speed of the thorium nucleus? So basically we start off with before a uranium, and then afterwards we end up with a small alpha particle shooting one way and the thorium nucleus shooting the other way. So we can use conservation of energy. Beforehand, we don't have any energy. We know energy before has to equal energy afterwards. Afterwards, we're going to have momentum or energy from the alpha particle. So we'll use 1/2 mv squared from the alpha particle, and we'll do plus 1/2 mv squared from the thorium nucleus. So we have to figure out these masses. They give us the mass of the alpha particle, but we have to figure out the mass of the thorium by subtracting from the original mass of the uranium, because this was the uranium mass. And that will give us the mass of the thorium. So it's 1/2 mass of the alpha particle, which is 6.68 times 10 to the negative 27, times the speed of the alpha particle, 2.1 times 10 to the 7 meters per second squared, plus, I'll write that a little bit below here, 1/2 mass of the thorium nucleus. Like I said, we have to subtract to get that, which gives us about 3.9 times 10 to the negative 25th. Take the uranium minus the alpha particle, times the speed of both, which we don't know, so we're going to call that's the speed we're looking for, speed of the thorium nucleus squared. So we're going to have to subtract this quantity to their side, and then we're going to have to divide by this and take the square root in order to find that speed of the thorium nucleus, and that gives us 3.59 times 10 to the 5th meters per second. Technically the book has this negative because it's going the opposite direction of what we call the positive direction, so I'm not going to be picky about that though. So the next question, number 9, says two cars in an icy intersection, the blue car with the mass of, so the mass of the blue car, write this down. Okay, so here's all the information they gave us. Mass of the blue car, mass of the red car, tells us that the blue car is headed east at 20 meters per second, the red car is headed north at 30 meters per second. The question is, they're going to collide, stick together, so what is the speed and direction of the cars as they skid away just after colliding? Okay, let's do the momentum in the x and the momentum in the y separate. So the momentum in the x before is going to be all from the blue car. So that is mass of the blue times velocity of the blue, which is 2,500 times 20 meters per second. And that has to equal the x afterwards, which is going to be both of them stuck together, which is going to be mass of both times the velocity of both in the x direction. Now the mass of both we know is 3950. So we're going to look for the velocity of both in the x direction, which we can find there from that equation. And if we do that, we get the velocity of both in the x direction is 12.66 meters per second. Keep in mind, that's the velocity of both in the x. Now we can do the y's. So in the y beforehand, what we have, I'll do this in a different color, is just the red one. So that'd be mass of the red times velocity of the red, which is 1450 times velocity of the red, which is 30. And that has to equal afterwards. So afterwards they stick together, so it'll be mass of both times velocity of both, but keep in mind that's in just the y direction. So mass of both is 3950 times velocity of both in the y direction. Divide both sides by 3950, and that gives velocity of both in the y is equal to 11 meters per second. And then I can make a triangle real quick, and now I know the x component, 11 meters per second, and the y component of their velocity, which is 12.66. I can do the Pythagorean theorem to find the overall, and I can also do inverse tangent to find the angle. And if I do that, I get, sorry, this is 11 and this is 12.66, I have to switch. Pythagorean theorem gives me 16.78 meters per second at 71.6 degrees north of east. Okay, the next problem is the last one, number 10. This is a tough one. We have to do break this up into x and y components. So in the x direction before and after. So before we have this one, where the x component would be 6 meters per second is, I'll do this in terms of momentum. So the momentum would be mass times velocity, which is 6, or 12, I'm sorry. So this would be 12 for the hypotenuse. So if you make a 45, 45, 90 triangle either here or here, where this hypotenuse is 12, these would be 12 divided by the square root of 2, according to our special right triangles. So basically, this x component down here is 12 divided by the square root of 2. So we got 12 divided by the square root of 2 for the x component of momentum from this one before. Plus, we've got the x component of momentum for this one, which would be 3 divided by the square root of 2. For if you make a right triangle here, where this is 3, these would both be 3 square root of 2, based on your special right triangles, the momentum vectors. And then afterwards, we have momentum from both of these. Now I'm going to break this up into a triangle right here, and we know this angle is 25 degrees, so we can find the momentum, the x momentum of this particle right here, which since this moves to the right with a velocity of 4.5 meters per second, it said, so that would be 9 for the momentum, multiplied by its mass. Momentum is mass times velocity. So if this is 9, then x component of momentum would be 9 cosine of 25. So I have 9 cosine of 25 plus, and then the other momentum, which is, we don't know. So I'm going to call that the x momentum of the 1 kilogram mass. I'll call it use p of x for that. It's a variable. We can solve for that. And then we're going to do the same thing for y. Y, these are the same, by the way, 12 divided by the square root of 2, because these are 45, 45, 90 triangles, so the y components are the same, only this one's negative since it's going down, so I'll make that negative. And then afterwards, I have the momentum from this one, which would be 9 sine of 25, for this y component right here, and that would be going down as well, so it'd be negative. Plus, and then I also have minus the momentum of this in the y direction, which would be that vector right there. So that'd be momentum in the y of the one I'm looking for. So I can solve both of these for p of x and p of y, and that gives me 2.45 and negative 2.45. I'm sorry, negative 2.56. And so I can set up a triangle then for my momentum for this one. I'll set it up like this, where the x is 2.45 and the y is negative 2.56. So I can figure out the angle. Actually, I'll set the triangle up like this so that you have this triangle right here, the one afterwards. So we have the momentum in the x, which is 2.45, and the momentum of the y, which is negative 2.56. That's the angle we're looking for. If we do Pythagorean theorem, we can get the hypotenuse, which gives us 3.54. And then if you inverse tangent, so inverse tangent of theta equals opposite 2.56 over hypotenuse 2.54 negative. That gives me this angle right here, which ends up being 46.3. So our final answer, if this is 46.3 degrees, is 3.54 meters per second. Actually, at 46.3 degrees below horizontal. And the other thing I forgot to tell you is that to get these are actually velocities in the x and velocity for the y. So when I found the momentum, I divided by the mass of each of these, divided by, well actually, they're the same because the mass is 1 to get these. So these are in meters per second. All right, I hope this helps.